Hey, hello out there. Let's see. I want to put the link now. Well, here we are. And you want to come up and talk? Well, let's. Hey, hi, Don. How are you? Long time no see. I hope you're doing well. Well, well, well. Look at this. Well, I'm gonna check this out. There's actually a live of space.
aftermath of the Big Bang, a monumental explosion that occurred approximately 13.8 billion years ago, we venture into an era where the universe was in its infancy, teeming with high temperatures and dense energy. This initial burst set the stage for the universe's formation, marking the beginning of space and time as we understand them. In the fleeting moments following the Big Bang, the universe was an incredibly hot and dense point. Within fractions of a second, it began expanding at an exponential rate, cooling as it did so, allowing for the formation of the fundamental forces of nature, including gravity, electromagnetism, and the nuclear forces. As the universe expanded and cooled, conditions became ripe for the creation of the first subatomic particles, such as quarks and electrons. These particles, born out of the energy from the Big Bang, eventually combined to form protons and neutrons. The universe, however, was still too hot for these protons and neutrons to combine into atoms. It wasn't until about 380,000 years after the Big Bang, as the universe continued to cool, that protons and neutrons began to combine to form the nuclei of the simplest elements, hydrogen and helium, through a process known as nucleosynthesis. Hydrogen, the most abundant element in the universe, and helium, the second most abundant, were the primary products of this early nucleosynthesis. Trace amounts of lithium were also produced during this period. The creation of these elements set the foundation for the complex chemistry that would eventually lead to the formation of stars, galaxies, and planets. As the universe continued to expand and cool, gravity began to pull together clouds of hydrogen and helium gas, leading to the formation of the first stars. These first stars played a crucial role in the evolution of the universe. Through nuclear fusion in their cores, they forged heavier elements such as carbon, oxygen, and iron. The life cycles of these stars, including their eventual explosion as supernovae, dispersed these heavier elements into space, seeding the cosmos with the ingredients necessary for the formation of new stars, planets, and eventually, life itself. The cosmic microwave background radiation, or CMB, is a faint glow that permeates the universe, offering a snapshot of the cosmos a mere 380,000 years after the Big Bang. This glow is not just a relic of the past, but a treasure trove of insights into the early universe, its composition, and its evolution. The CMB's discovery in the 1960s was a pivotal moment in astrophysics, providing strong evidence for the Big Bang theory. This radiation is the afterglow of the universe's explosive birth, stretched and cooled over billions of years as the cosmos expanded. Its uniformity and slight variations tell us a compelling story about the universe's infancy. One of the most fascinating aspects of the CMB is its astonishing uniformity. Across vast expanses of space, the temperature of this radiation is incredibly consistent, about 2.7 Kelvin or minus 270.45 degrees Celsius, with minuscule fluctuations. These minute temperature variations are crucial for cosmologists because they represent the seeds from which galaxies, stars, and eventually planets formed. Essentially, these fluctuations in density and temperature underpin the large-scale structure of the universe we observe today. The CMB also serves as a profound probe into the composition of the early universe. By studying its light, scientists can infer the universe's makeup at that time, revealing a cosmos filled predominantly with hydrogen and helium, the simplest and most abundant elements. This elemental composition supports theories of nucleosynthesis, predicting how the first elements formed in the universe's nascent moments. The polarization of the CMB light, akin to the way certain sunglasses can block out glare by aligning light waves, offers additional clues about the early universe. Another intriguing insight from the CMB is the glimpse it offers into the nature of dark matter and dark energy, mysterious components that constitute most of the universe's mass energy content. The way CMB radiation is scattered and its interaction with matter over cosmic timescales helps cosmologists map out the influence of dark matter in clumping matter together and the role of dark energy in accelerating the universe's expansion. In the wake of the Big Bang, the universe was a formless expanse of energy, primed to evolve into the structured cosmos we observe today. This transition from chaos to order was governed by the emergence and shaping of the laws of physics, fundamental principles that dictate the behavior of the universe. Initially, in the universe's first moments, temperatures were unimaginably high, and the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified. As the universe cooled, these forces began to separate, a process pivotal to the formation of the cosmos as we know it. The first to split was the strong nuclear force, responsible for holding the nuclei of atoms together.
Hey, hello,
This
Jane. How are
separation
you?
set the stage for the formation of the first subatomic particles, including quarks and electrons, mere fractions of a second after the Big Bang. As the universe continued to expand and cool, quarks coalesced to form protons and neutrons, the building blocks of atoms. This period, known as the quark epoch, was crucial for determining the amount and types of matter that would dominate the universe. Following this, the universe entered the electroweak epoch, where the electromagnetic and weak nuclear forces distinguished themselves. This differentiation was vital for the creation of various types of particles and antiparticles, and for the processes that led to the predominance of matter over antimatter in the universe. Without this asymmetry, matter and antimatter would have annihilated each other, leaving the universe devoid of the galaxies, stars, and planets we see today. As the universe aged, it cooled sufficiently for the first atoms to form, a phase known as recombination, occurring around 380,000 years after the Big Bang. This was a pivotal moment, as it allowed photons, particles of light, to travel freely for the first time, creating the cosmic microwave background radiation, a snapshot of the universe at that time. The laws of physics, particularly electromagnetism, played a crucial role in this process, dictating how electrons and nuclei combine to form neutral atoms. Gravity, the weakest but most far-reaching force, began to sculpt the large-scale structure of the universe during this period. Regions slightly denser than their surroundings began to collapse under their own gravity, forming the first stars and galaxies. This gravitational clustering is a process that continues to shape the cosmos, driving the formation of galaxy clusters and superclusters. Over billions of years, the interplay of these forces under the laws of physics facilitated the evolution of the universe from a hot, dense state to the vast and varied cosmos we observe today. Elements formed in the hearts of stars were scattered into space by supernovae, seeding the cosmos with the building blocks for new stars, planets, and eventually life. The laws of physics, emergent in the aftermath of the Big Bang, not only dictated the creation and behavior of the universe's fundamental particles, but also guided the evolution of the cosmos from simplicity to complexity. As we delve deeper into the mysteries of the cosmos, the process of galaxy formation and evolution stands as a cornerstone of
Hey, what up, Jamie? Come up, man. All right, man.
Welcome back to Science Click. Today, what would we see if we approached the speed of light? Let's embark together on a spaceship which accelerates away from Earth, moving faster and faster. What would we see when constantly accelerating? What optical effects would occur? And if we tried to exceed light speed by bending space-time like in sci-fi movies, what would we see? Answering these questions will lead us to explore many fascinating phenomena of our universe and immerse ourselves at the heart of special and general relativity. Our spacecraft is initially at rest. Once launched, we begin to accelerate. We imagine that its propulsion system allows us to accelerate constantly, as long as we wish. As we gain speed, we move away from Earth. By accelerating more and more, one would think that the speed would eventually become unbearable. However, this is not the case. Speed has no effect on our body. When two trains cross, it is impossible to feel whether it is our train or the other which is at rest. Similarly, inside the spaceship, we cannot feel its speed, but only its acceleration, the thrust of the reactors which presses us against our seats. If this thrust is reasonable, it will be perfectly bearable all along our journey, even when approaching the speed of light. There is nonetheless a risk associated with very high speeds, a collision. At high velocity, a mere speck of dust would cause colossal damage if it hit us. Fortunately, our ship is equipped with a force field that repels dangerous objects and allows us to roam freely through space. As we accelerate, a first optical effect appears. The stars in front of us, which we get closer to, seem to gradually move away. The sky contracts before us. To understand, think of this common situation. You are in a car driving at high speed, and it starts to rain. The rain falls vertically from top to bottom, but as the car moves forwards, you receive raindrops on the windshield from face on. The rain does not appear to fall from above, but from the front, as if its trajectory were tilted. And the more you accelerate, the more the rain seems to come from face on. In our spaceship, the optical effect is perfectly analogous. The stars' light comes from a certain direction, but as we accelerate, the light rays appear to come more and more from the front. Their direction seems different when we are in motion. This is the aberration of light. As light focuses in front of us, its intensity increases, while behind us, the sky seems to widen and becomes darker. The aberration of light results in another strange phenomenon. Let's imagine we are moving through an immense grid representing the fabric of space. Ordinarily, we would see a straight grid made up of straight lines converging in front of us due to perspective. However, by speeding up, the aberration phenomenon distorts the image of the sky around us as the days go by. The grid seems to contract forward, and the straight lines bend. If we were to go past an object, it would appear to be slightly angled in our direction. This is called Terrell-Penrose rotation. As we move very quickly, images of objects seem contracted in front of us, and perspective is strongly distorted. We often hear that the further we look into space, the further we look into the past. Indeed, the light we receive from a distant star must travel billions of kilometers. This journey is not instantaneous, and it takes some time for light to reach us. As a result, we see the star as it was in the past when it emitted this light, perhaps several thousand years ago. Who knows how it might have changed since then? looking out from our spaceship, the same phenomenon is at work. As we move away from Earth, the planet's light takes longer and longer to reach us. If we could zoom in with a telescope, we would see people on Earth evolving in slow motion. This is the Doppler effect. Each tick of the clocks on Earth takes longer and longer to reach us. We receive light rays in slow motion, and their intensity seems to weaken as the image of the planet shifts towards red color. In front of us, it's the opposite effect. The ship catches up with the light, and the stars seem to get brighter. They shift towards blue color, and their clocks seem to tick faster. With precise enough equipment, we could measure the aberration and Doppler effects since the start of our acceleration in space. However, if we decided to end our journey and return to Earth, these effects would have had no impact. They are only optical illusions due to the way we receive light while moving. After several hundred days, however, as the reactors push us ever faster, the ship begins to approach light speed. At such speeds, some phenomena will no longer be mere optical illusions. Real physical effects will kick in with irreversible consequences. Special relativity comes into play. A first consequence of relativity is known as time dilation. Our universe is a huge four-dimensional fabric called space-time, made up of 3 dimensions of space and 1 dimension of time. Inside space-time, all bodies trace a trajectory since they all advance towards their future. Before takeoff, our ship was moving in the same way as Earth towards the future. But by picking up speed and zooming away from Earth faster and faster, our trajectory gradually deviated from that of the planet. The axis we call time is no longer aligned with the time axis of people on Earth. If we decided to turn around and come back, our clocks would have measured a different time, and we would have aged less than Earthlings because our trajectories in space-time would have been different. Another key consequence of special relativity is called length contraction. When a body moves at close to light speed, its length gets contracted in the direction of its motion. From the spaceship's perspective, the entire universe is moving backwards. For us, the universe is contracted along our direction of motion. As such, the length of the journey to reach our destination is shorter than expected. We are not talking about optical effects anymore, but of a physical and concrete phenomenon. If we tried to reach a distant star, the journey would genuinely seem shorter to us. It would take less and less time the faster we move. Thus, contrary to popular misconception, it is in fact possible to travel thousands of light years in just a few seconds. And in the case where we would move almost at light speed, the journey would even seem instantaneous to us. For the people on Earth, however, several thousand years would have passed. Length contraction is a very real phenomenon. However, visually, it would be difficult to see. To understand why, imagine that we cross the orbit of a planet. As it moves very quickly towards us, the planet's length is contracted. But remember, the farther we look into space, the farther we look into the past. And from our perspective, the back of the planet is located further in space than the front of the planet. The image that we receive from the back of the planet has taken longer to reach us, so we see it as it was in the past. Even if it is contracted, the planet does not look like it because we receive the image of its back with a delay. Rather than contracted, it appears to be rotated. This is a phenomenon we have already seen, Terrell-Penrose rotation. When we move very fast and look to our side, the edges of the object around us seem shorter in the direction of motion. This can be interpreted either as length contraction or as a rotation, as a change in perspective. For the same reason, a person watching us zoom by would not really see our ship contracted, but rather rotated on itself. Over time, our field of view continues to contract. It intensifies in front of us while going completely black behind us. By accelerating more and more, we would perhaps expect to reach the speed of light at some point. What would we see then? This question might be one of the most fundamental in relativity. The answer is no. Even if the ship accelerates constantly, we will never reach the speed of light. That is because the speed of light is absolute. You may try to catch a light ray, but from your point of view, it will always escape at the same speed, the speed of light. You may accelerate as much as you wish, even if from Earth you would seem to approach the speed of light. From your point of view, you are still motionless, and light escapes inexorably. In short, it is strictly impossible to exceed or even reach the speed of light. At best, our ship will continue to accelerate forever, and our field of vision will continue to shrink ever more, until forming an infinitely bright spot in front of us, surrounded by a completely black sky. Almost at light speed, all optical effects would become extreme. As we catch up with light rays before us, they all seem to come from the front. Meanwhile, the rays behind us can never reach us. In our frame of reference, the universe would be extremely contracted, like a thin fabric that we would cross from side to side in a fraction of a second. For a person on Earth, we'd be moving at the speed of light. But for us, the trip seems instantaneous. We move infinitely fast. To conclude, nothing can ever move faster than light through space. But there might be a way to circumvent this rule. In fact, nothing prohibits space itself from moving faster than light. Indeed, the theory of general relativity teaches us that the fabric of space-time is dynamic. It can bend in multiple ways. We could thus imagine creating a bubble around our spaceship, which we would propel faster than light. This is called a warp drive in reference to science fiction. It would no longer be a matter of zooming a vehicle through space, but of propelling the fabric of space itself. Our ship would remain motionless, surfing on a wave of faster-than-light space-time. Such a structure may seem absurd, and indeed it is currently thought to be impossible to achieve. Producing a warp drive would require bending space-time with huge amounts of negative mass, a form of matter that does not seem to exist in our universe. That said, mathematics still allow us to model and calculate what we would see in such a situation. If we looked from outside, the warp drive would seem to appear out of nowhere. The curvature of space-time deviates the trajectory of light rays, forming a moving lens which splits into two, one part moving forwards and the other retreating in the opposite direction. Light travels slower than the warp drive itself. When it approaches, light has not yet had the time to reach us. And after it crosses us, we receive both the light which had not yet reached us and the rays which were.
Well, that was something, huh? Well, yes, yes, what can we done? Ah, wow, look at that.
Us on this terrifying journey through the dark web's most chilling stories. Don't forget to subscribe to our channel for more spine-tingling content. Stay safe out there, and never forget, evil lurks in the darkest corners. Good night, horror fans. Let's see, how do I begin this? Do I introduce myself first? I guess, but my name does not really matter now. All that matters is what I'm going to tell you. For now, you call me March. That is one of the only things I can remember right now. My mother used to call me that when I was younger, but now I am not even sure if that was my mother or my older sister. It does not matter. Just let me tell you what happened while I still have the memories. I remember dirt, papers, trash bins, and a big city in the middle of the state we lived in. My mother, my older sister, and I all lived in this tiny, cramped apartment on the sixth floor of our building. My older sister, Heidi, or was it Amanda? Yes, I am pretty sure it was Amanda. I am already starting to forget everything. I have to hurry up if I want someone to know that I ever existed. Anyway, My sister was always the one that took care of me since my mother worked all day and all night, only returning at midnight, exhausted and heading straight to bed. The poor woman was everything but happy. She could barely afford to raise my sister and me, and to top it off, she was addicted to multiple drugs. She was never abusive when she took them, though. She was just in an unresponsive state of mind. The addiction began 2 weeks after my birth, and that also makes it 2 weeks after my father's death. She could not cope with it properly, and thus, drinking and heroin were the only things that could properly help her, as she did not have the money for therapy sessions back then. Even though she promised herself and us that she wouldn't, she became addicted. Drugs are expensive, and she often spends a fortune getting them in order to satisfy her cravings. But she was a kind, caring person. Not really the motherly type. She thought that if she gave us money, we would be happier. She thought that giving us the money she earned would make us feel better than if she hugged us or talked to us. Her intentions were not evil, though. She was a good person who just simply did not know how to show empathy properly. One day, when I was about 8 and when my sister was 14, I got bored. She had to go to the grocery store, and knowing that I would likely have nothing to do, she gave me her phone, kissed me on the head, and left. Like always, my mother was working and I was completely alone. The sound of Amanda closing the door scared me, but as soon as I heard that she finally got out, I ran to my mother's room and started to record immediately. You see, when I was little, I used to film these videos where I pretended to be a journalist named Maya, interviewing imaginary politicians and celebrities I made up myself, which were, of course, my stuffed animals. Just as I got to interview the president of an imaginary country, which was strangely a big blue elephant in a pink dress, a notification popped up on my screen saying that I ran out of memory and that I should delete some photos or videos. Of course, I was not going to touch my precious interviews, so I just pressed on the screen to make the pop-up go away. I, being the clumsy little girl I was, accidentally tapped on Google Chrome and was greeted by a bunch of pictures of cute pugs and such things. Amanda loved those, and would always show my mom the pictures so she could convince her to get us a dog. My mom, being the responsible adult she was, always declined because we could not afford another mouth to feed, and having a dog was both expensive and exhausting. Yes, my sister was also a responsible person, but not enough to take care of a dog all alone, and my mother, of course, could not help her since she worked all the time. Once I got bored of looking through photos of tiny animals and puppies, I just typed down random letters into the search engine and searched. To my surprise, instead of a bunch of gibberish, the first article that popped up was some kind of website called The Butterfly Effect, and such a title caught my attention quickly. Back then, I did not really know what that meant, but now, I know more than I should. I clicked on it, expecting to see a bunch of butterflies, but instead, on the whole page was a big blue butterfly set on a black background, and at the top in white text rested the words, The Butterfly Effect, and beneath those was the alphabet and the search engine just like Google's. I was very naive back then, and that caused me to browse through 1,000 names, and every time I pressed on a new name, the butterfly changed colors. The pink ones were the prettiest, but the dark purple ones made me uncomfortable. When I zoomed in, there were white lines all over the butterfly which showed important events in that specific someone's life, their birth, and sometimes even their death was there, describing how they were born and describing how they met their ends. It always gave me the option to edit, but every time I tried, the notification which stated something along the lines of, "You are not the creator," popped up on the screen, so I gave up. Before exiting, I wanted to try out one more thing, searching up my name in the search engine, and so I did. The butterfly which showed up when I searched up my name wasn't blue, or purple, or yellow, it was pitch black with white lines. I didn't like that one bit, so I zoomed in. I saw pictures of my birth, my first birthday, I saw everything. I did not find it disturbing though. I found it cool because back then I was a stupid child and my brain could not process things like that and confirm them as unsettling in any kind of way, shape, or form. I remember everything so clearly now, like it was yesterday. Or maybe it was. I still don't have my memories all in the right place. Margot Sables was born was the first line.